Okay, good afternoon again, and welcome to the second lecture in the series. Today's topic will vary a little bit over yesterday's, but Professor Sagdeev will cover a little bit of what he talked about yesterday, just to tie it all up with the continuum. So I'd like to just not spend too much time here and welcome once again Professor Roald Sagdeev to continue on his lectures.
I think you're probably very informed about slight delay, but it was because of the fortunate event. Another indication how NASA is trying to implement rapidly focus on exploration component of its activity. So I'm not going into the details. Probably most of you would understand what happened. Let me do the following. Quickly go back to yesterday's topic, and then it would be easier to introduce the issue of future of electric propulsion within the context of a general approach of exploration. Okay, I need to go to my slides presentation. Okay, so if everyone agrees that one of the components of New Space Initiative is to bring international partners into the program, then there are certain rules and criteria, recommendations which could sound rather logical in dealing with international partners. So how one can make the best use of international cooperation? So that's probably the first criteria should be to make sure that each participating nation which is joining, let's say, coalition of the willing to explore the solar system would bring something of their own, something of individuality of each spacefaring nation, their expertise, and out of which most important would be to pick up something which would complement, of course, the leading role of US efforts, US technology. And of course, each country would have to pick up it in a way compatible with their national space priorities. And then there is a very important component. There is a real understanding now. I think we are at the historic junction. No more confrontation between robotic and human approach in the exploration, but rather to look for the best symbiotic approach in this way. So I would call it a balance between robotic and piloted exploration. Most of the partners, especially if you go beyond Russia and Europe, who have experience in manned flights, so most of the other partners probably would be, at least for time being, would be contributing to robotic component. And of course, the rule which must be followed, it's nobody expects United States to be, in this case, on equal footage with other partners. Clearly, we are the founders of the new initiative. the major contributor, major financial, economic burden, and it is understandable because even if you compare the budget of NASA with the integrated space budget of the rest of the world, you would understand that we are leaders and we will continue to lead international collaboration for many years and decades to come. And this immediately would dictate simple criteria. We should try to avoid to be dependent on critical paths, to technology, to integration of this type of mission. It is very sensitive, it should be done in a very accurate way. So there should be redundancy if some of the junior partners at certain moment would have a difficulty, like, financial default, the world is not immune to this type of changes. So it would not play as a showstopper. But it is, of course, very sensitive. We cannot tell to our partners that you are insignificant and we are not going to use you in important things. But it is a very delicate issue. I would, as a negative example in the past, I would quote one prominent member of Congress. At the beginning of International Space Station project, he once exclaimed, "We should not let Russians to be in the driver's seat in the space station." It sounded a little bit offensive for Russians. So I was debating that particular person. I said, look, you should change the language, because what you say now may sound ridiculous for those of Americans who had an experience to hire a taxi cab in New York, for example. Okay, let's go further. So now I'm going to talk about electric propulsion. Whatever is done and going on with electric propulsion in space now, it is completely 100% dependent on electric power we are getting from photovoltaic, from solar panels. And in a larger sense, it explains why we are now at such a modest level of trust, of use of electric propulsion in our particular space operation. With the exception of one outstanding but still small-scale NASA experiment, NASA Deep Probe, which was using ion thrusters for its interplanetary journey, anything else which was done in electric propulsion until now was not even intended to drive spacecrafts to new orbits, new locations. It's for 100% is related only to station keeping. In one particular application, station keeping for geostationary satellites. And the reason why it is related to geostationary is very simple. If you take any kind of telecommunication satellite on geostationary slot, it is a great idea which was suggested in 1945 by Arthur C. Clarke. At that time, he was a young officer at British Air Force, and he came up to such a wonderful idea. But when we say that the spacecraft in geostationary location is nailed to specific slots, so we could always see it in the same position in the sky, it is not true, because gravity forces of the sun and the moon, they gradually erode precise geostationary location of such satellites. So if such satellite would be left alone after being put in a geostationary slot, it would take a few months, maybe a year, finally to get it out of that precise geostationary location, and eventually the satellite would go by circling around figure 8 with increased amplitude, which is absolutely incompatible with uses of this fleet of satellites for telecommunication purposes. In order to compensate this negative influence of solar and lunar gravity, it requires from time to time to fire the engine for station keeping to bring it back to its original geostationary location. Delta V, the change of velocity accumulated over the say 1 year period, is quite substantial. It's about half a kilometer per second. And of course, commercial requirements are to keep such satellites in geostationary as long as possible. The standards are always growing. The clients would think even 10 years is not a good, so it would go further and further. So I'm sorry, for 10 years it would take half a kilometer per second. So 20 years a kilometer per second. If you would use a conventional combustion engine in geostationary, it would be even difficult to reach ISP typical for most powerful combustion rocket motors. So in most cases, it would eat substantial fraction of the mass of the geostationary satellites. So all these geostationary satellites operators gradually demanded that electric propulsion should be introduced for station keeping. Former Hughes, now Boeing, made the biggest strides. All the new generation of Boeing telecommunication satellites are using electric propulsion in form of ion engine. It's probably the highest existing power which is used to drive ion engines. The typical module unit of ion engine is about 5 kilowatts. It's the highest figure in use. Other satellite manufacturing companies also are moving to electric propulsion. I would expect that in a few years there would be no more geostationary satellite in usage which would not be based on electric propulsion for station keeping. With ISP of that existing engines, for example, Boeing's ISP, which is in use, is about 1500 or maybe even more second. So that means that the exhaust plasma stream, in that case, is a stream of individual ions, because it's ion engine, compensated by electric charge of the electrons, exceeds the speed of 25 or 30 kilometers per second. Russians are closely following after Boeing. They are using a different type of electric propulsion to provide for station keeping of the same, of their own geostationary telecommunication satellite. They are using so-called Hall thrusters. When you deal with electric propulsion, the options are, at the beginning at least, quite open. You can find configuration, how to apply electric field for electric power to accelerate the substance, charged particle of plasma, in such a way that each individual ion would be controlled by electric field created by the voltage difference created by the power source inside the thruster. So it's ion engine. And the higher is a thrust, the bigger would be the chunk of ionized gas plasma you would need to use for such electric propulsion. You cannot eventually separate individual ions. You have to operate with the plasma as a continuum. And then you have to move to a different design of the thruster. It's called whole thruster. Russians are especially experts in this type of thrusters. It requires the use of magnetic field to make sure that ions and electrons within the same substance would behave differently, so you would be able still to accelerate ions to high velocities. So these whole thrusters are now placed on almost every Russian geostationary satellites. From Russia, this technology of whole thrusters migrated to Europe. Europeans are moving toward electric propulsion in the final station at geostationary orbit. And moreover, it even migrated to United States about 12 or 13 years ago. There was a special joint venture created between Loral space system and Russian inventors of whole thrusters, and Loral is moving to electric propulsion for station keeping, and it's actually providing, it's a prime contractor of telecommunication satellites also for many other uses. For example, Intelsat, the major international satellite operator in telecommunication area, is a client of Loral. So now we see that the whole international community is moving. If you would ask me about Lockheed Martin, since a number of years ago was pursuing its own technology in electric propulsion, which is a little bit different. It is still in substantially lower ISPs, and I don't think it has a big future eventually. Why, despite of obvious practical success in the use of electric propulsion, it is not becoming the major instrument, major tool which can be applied not only for station keeping, but also for orbit race. The ideal would be to do the following. The conventional technique, expandable launcher or shuttle, could deliver that telecommunication platform or any other satellite to parking orbit at the altitude of a couple of hundred miles. And then the next step would be picking up by electric propulsion and moving it to wherever we would need it, either geostationary or heliocentric, planetary, whatever. But nobody ever tried it. Why it is so? This is now, we are coming to the important point about the drawbacks of contemporary electric propulsion, which is completely dependent on solar panels. First of all, you will have to deal with limited power on board of satellite. The solar panels cost money. They are heavy, even the best of them. So eventually you will have to deal with the limited power. The biggest power drawn from solar panels is on International Space Station, but considering the scale of operation, still it's quite modest. The next major consumers of solar power, use of solar power are big telecommunication satellites in geostationary, but no one yet exceeded 10 kilowatts of power. Most of them would stay in the scale of, in the range of few kilowatts of electric power. So not much to operate electric thruster. So as a result, what you have here, the mass saving mode is to go to as high ISP as possible with any existing electric thruster. For example, the Hall thrusters and iron thrusters can operate with ISPs substantially higher than, say, even 2000 second, or close to 2000 second. So, but as a result, the thrust at a given limited electric power is going down, inversely proportional to chosen ISP. Smaller the thrust, the next step is it would take ages to move spacecraft from geostationary, from parking orbit, low Earth parking orbit to, say, geostationary. If you would take specific parameters of Hughes's or now Boeing's major telecommunication satellites, the 700 series, which are using ion thrusters, it would take more than a year to move them from parking orbit to geostationary at that given electric power. And immediate result of it is no customer would agree to keep investment frozen in between parking orbit and geostationary for such a long period, especially considering that at the altitude of about 2,000 kilometers and higher, the spiraling satellite slowly raising its orbit would have to go through killing Van Allen belt, radiation belts. All these calculations and numerical simulations were made, and they indicate that there is no way to protect most valuable hardware on the satellite if satellite would stay for such a long period within Van Allen belts. And of course, the most vulnerable part are photovoltaic panels themselves. Whether it is made of silicon or more advanced photovoltaic material, it would immediately deteriorate the vacancies and defects created by incoming radiation. Protons as a most dangerous component, and then also electrons, it would be destroyed. And there is no way to protect photovoltaic with glass cover because it would take too much mass to build necessary shielding by transparent glass to protect photovoltaic panels. So there is another critical drawback associated with electric propulsion from solar panels, since power is limited. So as we understand, the satellite's orbit evolution from low Earth orbit eventually going to the moon or to heliocentric orbits would be not straight flight like it was done with Saturn V, or it is done with any extraterrestrial missions. It would be done in a slow spiraling with increased radius distance from the Earth. In such evolution of the orbit, the most important element is lost, which is called gravity assist. Gravity assist often is called gravitational swing by. It is used virtually by many interplanetary missions, especially those who would go to distant planets. The intermediate encounters with other celestial bodies like Venus or even with the Earth in a reverse trajectory could help to propel with a higher velocity further. But we are almost, we keep forgetting that launch from the Earth to Moon or planets, always the standard conventional launch, is also beneficiary of this gravity assist. When we have to get from parking orbit beyond terrestrial gravity, we have to spend only somewhat close to 3 kilometers per second escape velocity. Difference between 11 kilometers per second and 8. If we would do it with electric propulsion, with a low thrust typical for all of those type of systems based on solar power, we will have to slowly decrease velocity from initial orbital velocity at parking orbit close to 8 kilometers per second to 0 at the point where terrestrial gravity would become negligible. So in this case, in spiraling under the action of low thrust, the escape velocity actually is not 3 kilometers per second, but 8 kilometers per second. So again, moving to low thrust, we are using that gravity assist, and we have to pay the full price. No more gravity assist discount. So all of it actually tells that if we really want to use electric propulsion as a major tool in a new space exploration initiative, we would have to go certainly beyond solar power. And lastly, I wanted to mention another interesting thing, which probably few people thought in advance, but now we are confronted with an interesting new reality, new challenge to electric propulsion based on solar panels. This threat may be coming from solar sailing. If you take solar sail and compare it with a solar panel, so what is striking is the following. In solar sail, you have solar radiation, quanta of solar light, falling on, encountering the solar sail, and in the best case, reflected. So you have like a mirror, and at each collision, each quantum of solar radiation kicks the solar sail and the spacecraft with solar sail with double, twice of its momentum. So in electric propulsion based on solar sail, you do something different. You pick up solar quanta, digest it, absorb it, digest it, and convert its energy into the energy of electric thruster, which passes that energy to a heavier substance, to the ion. In most of the electric propulsion thrusters based on solar electric power, it is xenon, but heavy ion. So it moves with its own velocity. And then, according to the energy to which we accelerate. So now you can compare the momentum which this secondary ion is providing to the rocket with the momentum which is provided by absorbed or reflected solar quanta, and see what is the difference. The difference would be like a ratio of the velocities. The momentum which solar sail gets from reflecting solar quanta at a given same energy is smaller as a ratio of velocity of ion in electric propulsion to speed of light. And so everyone would say, oh great, there is a big difference, maybe 1,000 or more times in favor of electric propulsion. But then you have to introduce the following. While absorbing solar quanta to produce electric power, you are losing certain factor in efficiency of photovoltaic, which is between 10 and 20%, so almost 1 order of magnitude lost here. Second loss, the efficiency of thruster per se in accelerating the stream of charged particles, plasma particles, which could be also maybe 40, 50%, it depends on the type of the thruster. So then it would slightly change the competition between solar cell and photovoltaic panel in favor of solar cell, but still there is a factor of few orders of magnitude. But then, of course, the next question is, when you deal with the photovoltaic panels, you have to pay the price. It is still quite heavy, because you have to build not only structure, but you have to build the silicon crystal cells, connect with electric wiring to pick up the voltage from panel. And for solar cell, you don't need anything like that. You need to have very thin light material. So, and then suddenly you can overturn the ratio in favor of solar cell for the same given mass of the system. Until very recently, still competition was thought to be in favor of solar panel-based electric propulsion. Perhaps not anymore, and I will show you a few slides which indicate that there is an interesting new trend. Coming back to international partners. So with all the factors needed, all the criteria, we have to add political limitations or choices which we will have. We would need a degree of trust that any of our partners suddenly would not withdraw from our cooperation at the moment when they already would be given important essential slot. Then, of course, sensitivity in technology transfer is going to stay for a very long time with us. I don't know whether how much you are dealing it. Probably even international space station cooperation now requires special sensitivity in technology transfer. But even commercial space is having some problems because so much is required by restrictions on technology transfer. And then all of this would dictate to introduce individual differential approach to potential participants. So we can say, okay, we have allies, Europe, especially NATO countries, Canada, Japan, South Korea. And then Presidents Clinton and now Bush introduced notion of friends. Sometimes we call them strategic partners. And who are they? I think Russia. India recently became our strategic partner. I think Brazil probably likely should, maybe Franklin knows better. Should we keep Brazil as an ally or friend? Yeah, maybe ally, yeah. Ukraine, I'm putting here the spacefaring or countries with a space potential. Ukraine clearly is one of them, Kazakhstan, and Kazakhstan also is a strategic partner because in war on terrorism, Kazakhstan participates actively. They keep their small, modest, but still important contingency of their troops in Iraq, helping us. And then it's very difficult today to define a category to which we should relate China. You probably know that some people are skeptical whether we would ever become real friends with China. Maybe China is going to be our major future threat, depending on what's going to happen. But let me give you an example. Example of a major international project I mentioned yesterday. It's international controlled thermonuclear reactor. And it's a tokamak, it's magnetic field. Actually, it is an area which is very close to what Franklin Chandias was doing and is doing in plasma physics, and some of my activities were associated. So this is virtually this existing project. There are a lot of documents and countries are working. It is not that big as International Space Station, but there is nothing else except station in the same category. It probably would cost between $5 and $6 million, maybe more. It would consist of this test reactor as a huge machine to be built jointly, and I think by the end of this month the collaboration would have to decide where. And those who already are partners and they already claimed how much they will contribute. Europe 25%, Japan 25%. I think we are on a little bit modest level, 10%. But I agree with that. I don't think we should be number one everywhere in international area, but it's very important that we stay in touch. Russia is giving 10%, which is actually remarkable that, considering their economic situation. South Korea 10%, and you see now we have China already as accepted partner of major international undertaking. It can tell us that some changes might happen and we should be open to consider participation of China. But it's an issue of of course, of major political decision. Another interesting thing, another sign of China coming closer to international community is the fact that China recently was accepted as a partner of another major international undertaking. It is Galileo project initiated by Europe. It's probably you heard a lot about Galileo in conjunction of its potential competition with GPS, with American GPS. Hopefully this tension is now gone, and I think there is an understanding how GPS and Galileo could be compatible. But it's interesting that Europeans accepted China as a partner, not a full status, but a partner, and China pledged to contribute 300 million to development of GPS, and they're going to use it. So international spectrum of international alliances is very unusual. India, which is much closer to us than China, is not participating in Galileo, not now yet. And instead, I have discovered recently from interview which was given by Yuri Kopchev, Director General of Rosaviakosmos, that India and Russia concluded a major treaty on Indian participation in Russian version of global navigation satellite grouping, GLONASS. No, it's world is developing in a very interesting way. Let me go back to electric propulsion, back from politics. Several years ago, there was a huge excitement in Russia. Russians decided, following American initiative with electric propulsion from deep space, to use electric propulsion on a mission which would go to Martian moon Phobos, land there, and then even bring back the Phobos sample. And in doing so, they had a design based on Hall thrusters with a total electric power usable for propulsion about 3 or 4 kilowatts of energy. And if it would have been approved, it could be the major to date electric propulsion for robotic space exploration. However, there was a huge fight. All the arguments I was showing you about the drawbacks of electric propulsion based on solar photovoltaic power were used by opponents. And now Russian Rosaviakosmos changed its decision, and competing project was picked up, which has nothing to do with electric propulsion, at least at this stage. Let me just show you the general scheme. This is how they are going to fly now. It's interesting that the major workhorse in this mission to fly to Phobos and bring back the sample, again, is rocket, which is so familiar to you, the Soyuz rocket, with additional boosters, and you see here the whole scheme of flight. No electric propulsion is used here, except one optional case. I was also trying to persuade Russians that within the Mars system, electric propulsion could be used on a smaller probe, which would get captured in the Martian orbit, to maneuver from one orbit, from capture orbit, and so on, including encounter with Deimos, the second Martian moon. So I will skip this slide, which describes Soyuz launcher, except maybe one particular remark of political importance. US administration under Clinton was very conscious of the chance that Russian, former Soviet space technology legacy could be completely lost for humanity. And they made it clear that there should be certain cooperation to keep individual most crucial components alive. So Boeing was advised to build partnership with Energia, and Lockheed Martin was advised to build partnership with Khrushchev. And we see the fruits of these partnerships in International Space Station and also in other commercial projects. But one very important Russian asset was left untouched, the company which is making Soyuz and Progress systems. It's another known entity in Russia which is on Volga. It's called Progress Company. And a couple of years ago, nobody expected such a courageous initiative from President of France, Chirac. He flew to Samara, spent a couple of hours in this company, and what we see now, Soyuz rocket is going to be launched beginning with 2006 from Kourou launching site of France, of Europe now. So And I think, in my view, I feel sorry that at the time, 10 years ago, we did not pay much attention to this particular space culture, which built Soyuz and Progress systems. And now it would be in hands of France, in hands of Europeans, and eventually it would compete on commercial launchers market with American launcher systems. However, it may be a very important asset for new space initiative to have another critical launch site for the same proven technology as Soyuz rockets. So you probably know that Russians complemented Soyuz rocket with upper stage booster called Fregat. And I think if you would consider all the different upper stage boosters which may be useful for space exploration initiative, so Fregat should be one of the candidates to look more seriously. It's very compact. It can carry up to 5,500 kilos of fuel. It has a very good ISP, about the 330, very good for combustion-based engines. It allows multiple ignition, so, you know, several dozens, so it's really very good. For example, if one would imagine Soyuz spacecraft coupled with Fregat upper stage booster, it's already quite substantial exploration, crew exploration vehicle, which can be used, if not directly to the moon, but it could go clearly far beyond low Earth orbit and come back. When I was talking about use of what other countries can give to a new space initiative, I just got email from my Russian colleagues from my former institute IKI, how happy they are to contribute to Mars exploration program. You probably know that there was an interesting Russian instrument on Odyssey spacecraft which contributed to the discovery of water on Mars. So this is a map as Russians do it. And the interesting technology which was used in this experiment, in some of other experiments on Odyssey, especially the one from Los Alamos National Lab, they were using the expertise of nuclear scientists with the moderators in nuclear reactors. The neutrons resulting from cosmic ray irradiation of Mars surface can be moderated, slowed down in the material of the upper layer of Mars, just like in a fission reactor. And the best moderator is, of course, hydrogen. So the very presence of water can be immediately detected as a result of this evolution of the spectrum. And now what my colleagues are planning to do, they are doing test experiments. The Odyssey was using this technique from remote distance, from orbit, but eventually this type of technique could be brought to the surface of Mars. Perhaps it would become an indispensable instrument, tool in hands of astronauts. But in this case, you would not have to rely, you should not rely on cosmic rays, because intensity of a neutron flux would be too low if you deal with a specific location. So you have to bring a neutron source, or sometimes physicists would call it a neutron cannon, the little accelerator, which would, using different nuclear reactions, finally generate a beam of artificially created neutrons to probe the surface of Mars. So it would not be dangerous for the health of astronauts, for the crew. It's a very compact instrument. So this is how it would work in future. You see the neutrons coming down and creating the response. These much smaller energies of neutron coming back as a result of collision, being moderated by the material of Mars and measured by the detectors on, for example, on Martian rover. But it could be used also as a handheld instrument in future. That's probably very important for, in general, within the framework of exploration, looking for the water or traces of the water. So now I'm moving toward solar sail. I promised to say that why we think now that solar sail approach could be a threat to you see, I will come to it. You see the launch of the little rocket from submarine. And there is a specific project how such submarine-launched rocket can be used as an interplanetary vehicle eventually. So the Babakin Design Bureau designed the concept of using submarine-launched rocket to send little science payload like penetrator or a little payload landing softly on surface of Mars, only of a few kilos of the mass, but still the very fact that it could be done from submarine is very important. That tells you how it eventually would land to the Mars. So I will omit a specific example of electric propulsion for orbit race in a terrestrial environment. It's probably too specific for wider audience. So I would like to stop to talk about solar sail as a potential competitor with electric propulsion based on solar panels. So this is not somebody's science fantasy. It is a design which already was tested. It is going to be launched in September. It's a very small satellite launched from submarine, capable to deploy solar sail. Final mass of the spacecraft is 30 kilometers. Here you can also see that out of 30 kilometers, only a small fraction of mass would belong to this solar sail. What they are going to do in September to deploy at the altitude of 800 kilometers solar sail with the size of 1,000 square meters. So, which probably would be, you know, large fraction of this size of this audience. Okay. And if, no, I think it's now going back. So now the mass of this solar sail, which I don't understand why. Okay, go this way. Mass of this solar sail with a square area of 1,000 square meters is 5 kilos. It's today's technically feasible. It is already done, so it's going to be launched. So if you would consider how heavy would be a solar panel extended to 1,000 square meters, it would be several orders of magnitude for photovoltaic. So now For this little 30-kilo size spacecraft, there is no technology of electric propulsion which could compete with that particular design of the solar sail. So we are on the verge of reconsidering the use of electric propulsion based solely on solar photovoltaic power. And of course the argument that solar sail could not be efficient when you go far from the sun, the solar radiation pressure would go down as an inverse square distance from the sun. But same is true about solar photovoltaic power. It would go according to the same scaling law. So that's a very important argument to understand that why we have to move to non-solar photoelectric power. And there is only one source of energy, it's only the nuclear. Thank you.
Take some questions?
Yeah, absolutely. Yeah.
So we can open the floor for some questions if anybody has any. John?
Professor Sagdeev, there was recent reports in the news media about some submarine-launched missile tests that President Putin has been observing. And the second attempt to launch a missile didn't work. The first attempt didn't work. Have you heard of those? And what does that say about the readiness and dependability of the Russian sea-launched missile system?
I don't know precisely what particular type of rocket was launched at this test, but a few days ago, Russian military, Russian strategic forces have carried exercises of strategic readiness and organization, and they were planning to even to launch some of the to do some tests in ICBM's launches. So I think it's if it is only 50% reliability, I think it sends a serious signal. But at the same time, if I would have been on the place of Putin, I would go to very serious unilateral reduction. Why Russia is trying to keep balance, nuclear balance with United States, I think it is absolutely ridiculous.
Other questions?
The 5 kilograms for the 1,000 square meter solar array is very exciting. Could you tell us a little bit about this, the deployment and the structure of the 1,000 square meters and how it is maintained out there?
I don't know much of the details of this technology. I only know that the deal is the following, that Planetary Society, which contracted Russians, found American company, and this particular superlight material is coming from United States. And deployment system is invented, is designed by the Russians. So probably it would not be, of course it cannot be a rigid system, but at least, you know, it could collect the momentum from solar radiation.
Can you tell us more about the propellant for the solar-powered electric propulsion system?
I think almost in every existing electric plasma or ion thruster, they are using xenon gas, and xenon has a tremendous advantage compared to other gases, other materials, because of its ionization potential. to ionize, to make xenon ion usable for subsequent acceleration in the engine, you have to ionize. Energy which you invest in ionization, in taking electrons out of the orbit, eventually would enter into the equation for energy efficiency. So this is why for intermediate, for moderate ISPs, like in these thrusters, like 1500 or 2000, it is very important to use xenon. Even argon would bring energy efficiency from existing, say, 60% in the best machines to below 40%. And chemically, it's neutral, it's noble gas, it's much easier to keep it under control, and usually they are also keeping it pressurized, so it's almost liquefied, it's in a compact way.
Can you tell us what the smallest size of a thruster you've built?
The smallest whole thruster I saw based on a xenon was consuming something like maybe 200 or watts electric power. It's smaller, but I don't think it's already used. But the idea to develop such small thruster was to use it in a new area of small satellites or microsatellites. But thrusters which are used commercially on telecommunication satellites, the Russians are using 1 kilowatt unit. Boeing went up to 4.5, almost 5 kilowatt of power. So it's within this range. There are thrusters on test in a test chambers under development with a power up to maybe 40, 50 kilowatts. But I don't think this particular technology based on Hall thrusters could go beyond 100 kilowatts. The moment you'll have to go beyond, this is follow Franklin Chang Diaz.
The only two times I've heard of the Fregat mentioned in the news, it was associated with an inflatable reentry device that seemed to go wrong both times. Is that an integral part of Fregat, the reentry system, or is that a payload it was carrying? And can you tell me anything more about that reentry system?
Inflatable device is absolutely separate. It has nothing to do with Fregat. But Fregat is just, you know, multi-ignition type upper stage booster. It was used, for example, to launch